At least 9 identified mountains of Io are over 9 kilometers tall compared to their surrounding surface. So, at least 9 mountains of Io are taller than Mount Everest when compared to the sea level. The tallest mountain of Io is 17.5 kilometers above the surrounding surface. That is Boösaule Montes. So, it is not as tall as the tallest known planetary mountain, which is Olympus Mons on Mars at 21.5 kilometers. Still, this mountain is much sharper as it covers a surface area of 17,900 kilometers square, much smaller than the surface area of Olympus Mons, which is 300,000 kilometers square. That is similar to the surface area of Erosion or Italy. Most of the height of Olympus Mons rises gradually over a low-angle slope. However, at the outskirts of the mountain, near its edge, there are extremely tall, high-angle slopes. One of them even reaches a height of 10 kilometers, and it is visible from the position of a human or a rover standing close to the slope. However, Boösaule Montes is much more impressive in this aspect. Standing next to this mountain in the surrounding region, nearly the entirety of its height would be visible, so nearly the entirety of 17.5 kilometers. So, could we climb this mountain? Performing a safe landing at the top of Boösaule, or even close to the top, is very difficult, because it is very steep in a lot of areas. This is less true for Olympus Mons, which at the top has a huge flat area, its caldera, which has a surface area of about 3,000 kilometers square. These form after magma below the surface is emptied and the surface above collapses. So because Boösaule doesn't have a huge flat area at the top, we have quite a bit more incentive because of that to just climb the mountain. So how would we go about doing that? Two very obvious problems are presented with this mission. The most obvious one being that we currently have no way of safely delivering astronauts close to Io. The health effects of a several-year trip to Io would need to be mitigated, and the resources for such a trip are also going to be a problem. And even if we somehow could solve the issues with multi-year space travel, there is a second massive problem, and that is the massive amount of radiation that is present on the surface of Io. It simply doesn't allow us to venture out onto the surface such that we can climb mountains. A daily dose of radiation that one would receive on Io is 36,000 millisieverts, enough to kill anyone in a regular pressurized spacesuit in just a few hours. The radiation is so intense that it even damages some minerals on the surface, and it can mess with some spacecraft systems. Also, it is very much possible that it is a lot easier to invent a thing that can precisely land at the top of mountains of Io than to invent protection from the intense radiation that also allows humans to be flexible enough to climb Io's mountains. The Apollo astronauts which were on the moon allowed us to see that their pressurized suits in large part made them very inflexible. Take a look at what this astronaut needs to do in order to get up after falling. Part of the inflexibility could be due to low gravity, but certainly the very bulky pressurized suit plays a major part. Now, that suit protected them from the vacuum and the temperatures, but radiation wasn't really taken into account because on the moon it simply isn't all that deadly on the timescales of just days. The longest stay on the surface of the moon was 75 hours by Apollo 17. Although the level of surface radiation isn't even close to being similar, Io and the moon have a similar surface gravity. Both of them have about 17% the strength of the surface gravity of Earth. Both are also without an atmosphere, so both require pressurized suits. But Io on top of that requires some truly incredible protection from the radiation. So then let's say we do have it, and yet can still somehow move around like the Apollo astronauts on the moon. Reaching the top of Io's tallest mountain obviously depends on the route that we take. Climbing the mountain directly from its southern slope is probably not the best idea, as the slope there is extremely steep. Even if climbable, it is probably still extremely exhausting, even with the low gravity. This very crude path to the top is much easier to take on. The slopes here, although likely very steep, are still probably very walkable. So in total, the path from base, that is 0 meters, to the peak of the mountain of 17,500 meters is about 75 kilometers. The average walking speed of a human on Earth is about 5 kilometers per hour. But considering that we are going to be going uphill, are in a pressurized suit, and are going to need to carry a lot of stuff, we can easily put the average walking speed during this mission at around 1 kilometer per hour. Since daytime on Io lasts about 20 hours, and nighttime also lasts 20 hours, during daytime, 10 hours in total could be spent on walking, with a 1 hour rest between each interval of 1 hour of walking. Then for the next 20 hours, during nighttime, that time could be spent to set up a temporary camp for rest. At this pace, it would take us about 320 hours to reach the top of Boösaule, so 8 Io days, which is 13 Earth days. Now the sleeping schedule for us is going to be very messed up, because we are essentially going to need to stay awake for 20 hours during daytime, as that is the only time during which we can climb. And we need to stay awake for so long, many times in a row. So our sleeping pattern is not going to be aligned at all with the 24-hour cycle that our bodies are used to. That is almost certainly going to lead to some level of sleep deprivation, although probably not enough sleep deprivation such that it is dangerous. Now the weird thing about this whole climb taking 13 days is that is a lot less time than it takes for people to climb Mount Everest. And that is because people that climb Mount Everest need to spend many days on just getting used to the low oxygen environment as they go higher and higher. While with the Boösaule climb on Io, we are always in a pressurized suit. So then what about food, water, and oxygen? How much would we need to carry? For food, that depends on the type of food that we are carrying. Carrying a bunch of fat around is lighter per calorie than protein and carbohydrates. But let's assume that the food that we are carrying has an even split between the 3 macronutrients. If we assume that a person traveling is 70 kilograms, then considering that we are going to be pretty active on this mission, about 2,300 calories a day would be just enough so that a person doesn't lose weight. So if we assume that the food that we are carrying is split evenly between protein, carbohydrates, and fat, then 2,300 calories is about 470 grams. So in order to be fed for 13 days, a single person would need to carry at the start of the mission about 6 kilograms of food. Then obviously the amount of food carried is going to be decreased as the mission goes forward. For water, because we are going to be quite active, per person 3 liters of water a day should be enough. So in total, we are going to need to carry about 40 kilograms of water at the beginning of the mission. With food and water comes another problem, and that is how to ingest them and then how to dispose of the waste. The Apollo suits did provide a drink valve, which allowed Apollo astronauts to drink water on the moon by turning their head around and sucking on a straw-like tube. Starting with Apollo 15, along with water, there was a piece of food as well, a fruit bar that they could eat by turning their head around in a certain direction, although it is really not a very significant quantity. The suit for mountain climbing on Io would need to be modified such that food and water can be delivered on a much more significant scale. And on top of that, it would need to be modified such that food from outside of the suit can be delivered into the suit without destroying pressure. Along with that, there would need to be a system where human waste could be discarded without exiting the suit. The suit would also need to be upgraded so that it can provide total darkness for sleep. Now, the climbing mission should start at dawn, so that we have full 20 hours ahead of us where we can climb, and then after that, for 20 hours, it is nighttime, during which we can sleep. So then why is there need for the suit to provide total darkness if we are going to be sleeping during the night anyways? Well, because of Jupiter shine. On or near Boösaule, a part of Jupiter is visible. It is also fixed in the sky because Io is tidally locked. It needs the same amount of time to rotate around itself as it does to complete an orbit around Jupiter. Because a big part of Jupiter is visible from the surface of Io near Boösaule, during certain times, the sun-facing side of Jupiter is going to reflect so much light that the surface of Io is going to be visibly illuminated during night. That is certainly enough to ruin sleep quality. So a visor that can be pulled down to provide darkness for sleep is a good idea. The Apollo suits did have two visors for protection from the sun. The outermost one was even coated in gold, but they were designed so that the light bouncing off of the surface of the moon isn't disruptive, not so that they could sleep in their suits. Sleeping was done in lunar modules. For Io, carrying around a huge module while attempting to climb Boösaule is, well, extremely impractical, so sleeping in the suit would be necessary. Obviously, we would also need to lay down on the surface of Io to get rest, so the suits would need to be designed so that, at least while laying down sideways, nothing gets punctured. Laying down on the back probably isn't going to be possible because of the life support system. For oxygen, the amount that would need to be carried for 2 days is about a 14 kilogram oxygen cylinder, and that is the total weight of the cylinder, including oxygen. Now, the average adult at rest consumes about 0.2 liters of oxygen a minute, so considering that we are going to be active, an average intake of about a liter per minute seems fair. So that means that a 14 kilogram oxygen cylinder would last us for 2 days, which then means to reach the peak in 13 days, a total of 90 kilograms would need to be carried at the start of the mission per person. Then, as the mission progresses, empty cylinders are going to be discarded, so that is going to significantly change the amount of mass that is carried. We would also need to carry our pressurized suits with us everywhere we go. The Apollo suits had a mass of about 80 kilograms, so we can use that as a reference point for the mass of our suits. In order for the suit to be fully functional, besides the mentioned necessary upgrades such as the darkness visor and the ability to restock the suit supplies without exiting the suit, there would also need to be a way to get energy into the suit without exiting it. The Apollo suits had lots of electrical systems that regulated pressure, humidity, temperature, and so on. One way that the suits could be powered is maybe through the same source that powers the rovers on Mars. Curiosity and Perseverance are powered by plutonium-238, a radioactive isotope. The heat released through the decay of this radioactive element is turned into electricity to power the rovers. For Curiosity and Perseverance, the generator used is about 45 kilograms, and it contains about 4.8 kilograms of plutonium dioxide, and it generates about 110 watts. Certainly something would need to be modified about this generator so that the suits can be powered for 13 days, but the generators that already exist give us an approximate number of how heavy our energy system could be. Potentially some other things would also need to be carried, like lithium hydroxide, which removes the buildup of carbon dioxide in the suit due to exhaling. That's the substance that was used for the Apollo suits. But the total mass of lithium hydroxide that would need to be carried shouldn't impact the overall number all that much. So this seems a bit weird. Per person there's 6 kilograms of food, 40 kilograms of water, 90 kilograms for oxygen, 80 kilograms for the suit, approximately 50 kilograms for the power source. Then doesn't that mean that in total we would need to carry about 266 kilograms? Well, we wouldn't actually need to carry all of that. Only the suit would need to be carried at all times. A separate compartment on wheels could hold the food, water, oxygen, and the power source. And that is going to be about 186 kilograms. The wheel compartment is also going to add to the mass. Same is also true for the material in which food and water is stored. So maybe it is fair to add 30 kilograms on top of those 186. So 216 kilograms in total would need to be pulled along with us, which is equivalent to the mass of about 40 kilograms pushing down onto a scale on Earth. So while not pulling anything around, but rather just standing on Io, we would actually feel much lighter than on Earth, even with the suit. Assuming we are 70 kilograms and that the suit is 80 kilograms, we would be about 150 kilograms in total. So while stepping onto a scale on Io, we would see that the scale is showing that we are just 28 kilograms. Now, our mass would remain constant, which is 150 kilograms for the suit and the body, but scales determine your weight in kilogram force, meaning through the amount of force being exerted onto the scale. So of course, they are going to show your weight in kilogram force as being lower on Io. In terms of navigation, probably some satellite-based information could be useful to have in some scenarios, so it would be good to have it just in case. But that doesn't mean that it is absolutely necessary, as most of the mountain would be visible at nearly all times during the day, making the path towards the top not all that hard to figure out. As for what the hike to the top would feel like, for the first 10 to 20 kilometers, pretty easy, because of the low angle slope. That is, assuming we are excluding this one. Then the next 50 or so kilometers would be much harder, as those 50 kilometers are very steep. The wheel compartment that would be pulled along with us on the climb is going to weigh us down constantly. That's especially a problem in the steeper sections. So during pauses between climbing, the wheel compartment could be made so that it is anchored, so made stationary in such a way that it doesn't weigh us down on a high angle slope during rest. It is similar to pulling a handbrake in a car while on a hill so that it doesn't roll down accidentally. It's hard to say what stepping on the ground of this mountain would feel like. The surface of Io is coated in sulfur and sulfur dioxide, but the mountains are likely not made up of those compounds, as they cannot support such tall and rigid structures. Likely the mountains are made up of silicate rock. However, it might be the case that this rock isn't exposed in all parts, and that the mountain is still coated in sulfur and sulfur dioxide, despite structurally being made out of silicate rock. Because of the uncertainty with regards to what the terrain is like, the sorts of boots that are appropriate is also not known, although probably the ones that were used for the Apollo missions on the moon would do the job. So we reached the top of Boösaule Montes. At the peak, looking into the distance, the curvature of Io would be very obvious. It is much more obvious than being on Earth at an elevation of 17.5 kilometers, because Io is much smaller. From the top of the tallest mountain on Io, over the horizon, a part of Jupiter would also be visible, appearing many times larger than Earth does from the moon. Despite being able to see around 200 kilometers into the distance from the top, no other mountain would be visible. But what could be seen from that height is none other mountains, but rather a massive plain, which is actually the typical landscape present on Io. Most of Io's surface is a flat plain dotted with lava lakes and the occasional mountain, which is extremely tall. Looking southwards from the top, a slightly reddish hue would be visible on the ground, as in that direction is where the Pele volcano is located, which clearly blanketed the region with its eruptions. This volcano also has a lava lake. This infrared image reveals the heat present. Also close to these lakes is the huge Danube mountain that rises 5.5 kilometers above the surrounding terrain. Despite being much shorter, it has a surface area at least 2 times greater than Boösaule. This mountain consists of 2 elevated plateaus. In the middle of this mountain is also a huge canyon. So there is one pretty big problem with our whole mission to reach the top of Boösaule, and that is that this was a one-way trip. All of the supplies mentioned so far were what was necessary to reach the top, but not to get back down. That would simply double all of the necessary resources and would make the climb not really doable, as it would be far too exhausting, although maybe some modifications could be made such that the climb is possible. Io's mountains are unusually tall. It has about 155 identified mountains, with an average height of 6 kilometers. However, somewhat surprisingly, most of them are not volcanoes. The volcanic lakes, or volcanoes in general on Io, don't rise like they do on Mars. The previously mentioned Olympus Mons is a volcanic mountain, and Mars also has 4 other insanely tall volcanic mountains that rival Boösaule Montes in its height. But on Io, volcanic mountains only go up to a few kilometers at most. Nearly all of Io's volcanoes are almost flat. On top of that, Io's mountains are much more unusual than even mountains on Earth, and yet for both Earth and Io, the mechanism of formation is related to tectonics. But there certainly are still massive differences, which is why the mountains of Io look so strange. As to what the exact mechanism of formation is for mountains of Io, that still isn't known. The crust of Io is probably extremely thick, which is why it can support such extremely tall mountains. But these tall mountains aren't all that long-lasting. Io's surface is constantly being renewed because of geological activity, and future mountains will appear. But just like future mountains will appear, mountains of Io also disappear, and they do so through erosion, that is mass wasting, the process through which the rock of the mountains, bit by bit, gets detached and rolls down the slopes. Eventually, that leads to mountains being completely erased. So it is because of that it is very much possible that in the distant past, for example 2 billion years ago, that there was a mountain even quite a bit taller than Boösaule. And yet, because of the extreme geological activity, there isn't even a single trace left of that mountain. But what about climbing other mountains? The mountain of Io that we currently have the best photos of is Hi'iaka. Compared to the surrounding floor, its tallest peak is about 11 kilometers tall. The entirety of this mountain's peak height would be visible from the position of a rover or a human standing several tens of kilometers away from the peak. This is a semi-topographic map of Hi'iaka. It reveals that the two plateaus that it has are about 3.5 kilometers above the surrounding surface. In total, the two plateaus have a surface area of about 17,000 kilometers square, similar to Boösaule. So then what about rock climbing? The smaller of the two plateaus has extremely steep slopes. In some areas, they are pretty much cliffs, but cliffs that are 3.5 kilometers tall, much taller than any cliff on Earth. Just to give an idea of how tall that is, one of the tallest cliffs on Earth, if not the tallest one, is Mount Thor. It is located at one of the islands in the Arctic. The total height of this cliff from base to peak is 1.2 kilometers. It isn't known how dangerous it is to climb the cliffs of Hi'iaka. We don't really know if the materials on the cliff are stable enough to support safe rock climbing. But beyond that, rock climbing in a bulky pressurized suit is at the very least going to be challenging, if not impossible. On top of that, the climb could easily be much longer than the one on Boösaule, despite the much shorter height. Because this is, after all, rock climbing. It's going up a nearly vertical wall. So because the length of time necessary to climb to the top could easily be longer than to climb Boösaule, the resources to climb Hi'iaka's cliffs could even be greater, which tells us that the climb is pretty much not possible, at least with current technology, and also including the imaginary radiation protection. If we somehow were flexible and yet not in a bulky suit, while also carrying a crazy amount of supplies, then the lower gravity would make it a lot less exhausting to climb. And on top of that, falls would be less deadly than on Earth. On Earth, falling from about 20 meters is almost certainly deadly. However, falling from 20 meters on Io is easily survivable. It is similar to falling from just 1 meter on Earth. However, falls above 20 meters of height on Io start to get rapidly deadlier. While on the top of one of Hi'iaka's plateau, the view from there would allow us to see the massive lava lake that is 70 kilometers across. Maybe even the tallest peak of Hi'iaka would also be visible. It's 11 kilometers above the surrounding floor. The topographic map reveals that its height rises very sharply. It's hard to say whether or not it is walkable. Possibly not. Although maybe it is, with certain sections requiring hands to an extent for support. Whether or not rock climbing is required is hard to say. Another notable mountain where it's hard to say as to whether or not it requires rock climbing is Monte Bello. This mountain is 8.5 kilometers tall. From this angle, it does appear to have cliffs, so rock climbing is seemingly required from this position. But there are potentially other routes, not illuminated here, that would allow us to reach the top without rock climbing. Boösaule Montes is another mountain for which it is very hard to say as to whether or not rock climbing is required. It is about 5.5 kilometers tall. From this angle, the top view, climbing to the top seems doable without rock climbing. But this image reveals the actual topography. The peak is incredibly steep, and it likely does require some rock climbing. From the top of Boösaule Montes, what could be seen in the distance is a lava lake that is surrounded by this complex mountain. For some reason, big mountains of Io are frequently right next to lava lakes. For Hi'iaka, there is a very good chance that at one point the two plateaus were connected. That's why the shapes and the height of the two plateaus fit together so well. Then they started spreading apart, and eventually between them formed a giant lava lake. Boösaule Montes is another mountain on Io for which likely the similar geological process led to the mountain being torn apart with a giant lava lake appearing between the two plateaus. This mountain has a maximum height of about 7.4 kilometers. As for a mountain which certainly requires rock climbing, the Steeple Mountain is one of them. It was recently discovered. It was found through the images captured by the Juno spacecraft in December of 2023. It has one of the sharpest known peaks in the entire solar system, and the peak is revealed by the shadow that this mountain casts. This is an artist's concept of what is going on here. And considering the shadows, this is likely a pretty accurate depiction of what this mountain looks like up close. The rock climb to the top would be incredibly long, as this mountain is 6 kilometers above the surrounding surface. So, as we can see, many mountains of Io require rock climbing to climb. Io probably has the highest density of mountains in the solar system that are very exciting to climb. However, at the same time, they are also, at the moment, impossible to climb with currently available technology. The surface radiation problem of Io could be such that even long after colonies are established on Mars or even Titan, Io could still at that point be completely untouched by humans. Even for humans in such a distant future, climbing Io's mountains could also for them be, as well, just a distant dream.